Our next speaker is Roberto Bondesan from Imperial College London. He will join us virtually here. He has a PhD in theoretical physics, and during his studies he studied novel materials for electronics and quantum computing at the universities of Cologne and Oxford. After his PhD, he moved to Qualcomm AI research to work on quantum machine learning and the application of AI to design optimization problems. Recently this year, he joined the Department of Computing at Imperial College as a senior lecturer in quantum computing. His current research interests are quantum algorithms as well as machine learning for simulating quantum physics. And yeah, I would hand over to the speaker now.
All right. Thank you very much for the nice introduction and for inviting me to this very interesting workshop. Let me just start with introducing my talk. So the title of my talk is Quantum Probabilistic Neural Networks. And this is the agenda for the talk. So I will start by introducing some basics of quantum computing. We already heard in the previous talk a good introduction. I will just review some of the notions that I'm going to use later on. Then I will focus on quantum neural networks, in particular realized in terms of qubits, presenting some of our work there. And then switch gears and move on to photonic quantum neural networks. We heard the question just before about that, so hopefully this is also an interesting area for you. And finally, I will conclude with highlighting some of the future challenges. Okay, so let's start with some background of quantum computing. So first of all, quantum computers are believed to have exponential speedups for cryptography for the simulation of quantum physics. We also know that they can have speedups in a polynomial type for searching and optimization. And so on top of indeed the wave being a prominent example of those, there has been recent progress in the context of building a universal quantum computer. And in particular, this has been demonstrated recently, 2019, by the Google team, where they showed advantage for the task of sampling a random circuit. And the field has been progressing very, very fast recently, and this experiment was for 50 qubits, and now IBM has computers which have hundreds of qubits. And one of the overarching questions in the field is how are we going to use these early computers, and in particular, can we use them for machine learning? Machine learning being, of course, one of the main directions in computing in general. As I mentioned before, I would like to start with some basic notions indeed of quantum computation. And just to remind you perhaps what you heard before, or just to tell you if you just joined. So please bear with me for a couple of slides. So I would like to think about to think about quantum mechanics, which is indeed the physical theory underlying quantum computation, as a generalized probability theory. We are all familiar with the bits and the probabilistic bits, namely two-dimensional vectors of positive numbers A, B, which sum to 1, where A is the probability of the bit being 0, and B is the probability for the bit being 1. And you can visualize this in the plane AB as the following segment. Now we can start to think about quantum bits or qubits as two-dimensional vectors, which are now complex. So A, B are complex numbers, and they are such that the norm of the vector psi, namely absolute value squared A plus absolute value squared B equal to 1. And so if you now project it, say, on the real A-B plane, you will see that we go from this segment to this circle, meaning that we have enhanced somehow the space of possible states in this generalized probabilistic theory. Just give me 1 second, I need to move my Zoom. Okay, good. Moving on. The next bit that we need to know is about quantum gates. So we are now thinking about quantum computing or quantum mechanics in particular here as a as a probabilistic theory, and so it's natural to define evolution as some operation that preserves the probability. And so here we define evolution as a linear transformation that preserves the norm squared of these vectors, namely a squared plus b squared. So we can go from a state psi, so we call these probability vectors in quantum computing also states. We move from a state psi to a state phi by the action of the unitary matrix U. And the fact that U is unitary and not stochastic, like you will have in real, somehow in classical probability theory, can bring some new phenomena, in particular quantum interference. For example, if you take the following matrix here, which has a -1 in this entry, which is a unitary matrix, you can see that it acts on the state 1, 0, which is a state that is deterministic, which means that your particle, your bit is in 0. It moves it to a state that is probabilistic, which is a mixed state, which has probability 1/2 of being in 0 and 1/2 of being in 1. But then you can see if you act again with this U on this state, you will go to another deterministic state. So this is something that is not possible classically. It's called quantum interference, namely the cancellation of these probability amplitudes allow to do more interesting phenomena. And then on top of the unitary evolution gates, we also have the measurement gates that allow us to sample from these probability vectors or this state psi. And as we heard before, the outcome of a measurement is that your state will be projected onto one of these deterministic states or classical state X, where X can be either 0 or 1, with the probability that is given by the corresponding entry in this two-dimensional vector. So a squared will be the probability of this being 0, and b squared, this probability of being 1. And so the generalization now to n qubits is also, we heard it before, but let me just say it again, that if you go to n qubits, the quantum states you need to deal with are now not anymore superposition of 0, 1, but superpositions of bit strings of length n. And as you know, there are 2 to the power n possible bit strings of length n, and therefore these states will become exponentially large. While you can store these exponentially large states in n qubits, so in a number of resources that is linear in n on a quantum computer, classically in general, you cannot do this efficiently, and so you need to have these exponentially large vectors, and that's why it is hard to reason classically about quantum computation. And that's where the advantage of quantum computation comes from. So let me now move to quantum neural networks. So first of all, there is a very rich interface between quantum computing and machine learning, which is typically called quantum machine learning. And in the literature, we can classify different approaches in terms of the data type and the algorithm type. You can see here, for example, in this box where the data is classical, think about, image classification or something like that. And the algorithm is also classical. However, in quantum machine learning, it means that this is an algorithm that has been developed mostly by physicists to deal with the study of quantum physics. In particular, here you can see an example of a tensor network. Another type of approach is where the data is quantum, but the algorithm is classical. And an example here is that the data could be the implementation of a given unitary as a quantum circuit, and the algorithm then can be, for example, a machine learning algorithm or reinforcement learning algorithm that, given this unitary, tells you how to implement it. There is also this box where the data is quantum and the algorithm is quantum. And here the quantum data typically one wants to look at is the output of some physical experiment. For example, you can compute some property, some state that is describing a certain molecule. And then the quantum machine learning algorithm, what it will do is it will try to predict some of the properties of this molecule, given the physical realization as a quantum state. And finally, we go to the focus actually of this talk, which is where the data is classical and the algorithm is quantum. Again, think about, for example, image classification. Here you see an MNIST digit. And the idea is that we can try to embed this classical data on a quantum register, on a quantum computer, and then process this data with the quantum computer to solve some of the machine learning tasks that we would like to solve. So in more details, this is how we can think about a quantum neural network, namely as a variational quantum circuit. So we start at the left, and I introduced this graphical notation in the first slides of my talk. Let me just repeat it here. These lines here represent qubits, or your computational units. These boxes here represent operations, in the quantum computing case, unitary operations. And then this symbol here is a quantum measurement. It's when we extract information from a quantum computer that is then extracted as a classical bit stream. So variational quantum circuits for processing classical data typically look like that. You have some classical input X. Think again about your MNIST digit or any image you want, or any time series or classical data you want. This is now a parameter of an encoding unitary, which we denote here by U encoding. And at this point, your data in this circuit where time flows from left to right, at this point, your state of the system is an encoding of the classical data. And what we do then is we just apply a sequence of layers like you do in a classical neural network. But now these layers are not classical computations, but they are these unitary matrices that act on the space of n qubits. As you notice here, we have L layers, and so we denote the matrices U1 to UL. And these matrices are parametrized. So there are parameters or angles, theta 1 to theta L. And now the idea is that after we do a quantum measurement, we extract from the quantum computer some classical bit stream, some data. And now we can try to interpret this data, y hat, that we extract from the quantum computer as our prediction. And then we want to minimize the loss, for example, in a regression task, the MSE loss, between a ground truth y and the prediction y hat. We minimize this quantity as a function of the angles or parameters of the quantum circuit theta. So just really analogously to what you would do in the classical neural networks, where you minimize the weights that here are represented by theta to find as small as possible loss. And here on the right, you can see an example of what this quantum neural network will look like. Here I draw these big boxes, but in practice, the art of constructing these quantum circuits, like in classical cases, try to find the right, basically inductive bias or architecture in such a way that what you are trying to predict can be easy to optimize. So here is an example, as I was saying, where maybe you have a gate which now is a unitary operation that acts on the first qubit on top and the third qubit on the bottom. Then you have another one with different angles, for example, a different unitary that acts on the first two qubits. And finally, a third one that acts only on the third qubit. This could be an example. But now, introducing this kind of new paradigm, of course, poses a lot of questions. So the philosophy here will be that we don't have at the moment quantum computers to run, if you want, this any quantum neural network we want, because we are limited in size and other things I will tell you later on, in particular noise. But we can start to prepare to a future when we will be able to do this. And so we would like to start thinking, for example, what are the good quantum neural network architectures for different tasks? And also, interestingly, we have defined now this quantum neural network as a series of unitary matrices. We know that classical neural networks are quite different. They are typically linear, non-linear layers. And so what is the relationship between classical and quantum neural networks? That's also an interesting question. And finally, also, we know that quantum computing is basically implementing a probabilistic algorithm. So how can we use those probability in classical machine learning? Is there a natural way to exploit the inherent probabilistic nature of quantum mechanics to our advantage. And also, of course, we would like to understand how can we benchmark these quantum models. So in the remaining of my talk, I'm going to try to answer some of these questions, presenting some of our work in this area. So first of all, I would like to discuss an approach that tries to use the probabilistic nature of quantum mechanics as an encoding of probabilities over weights. So on the left here, we see an architecture which I call a probabilistic binary neural network, which is a classical architecture where you can imagine that the neurons and the weights in your architecture are discrete and binary variables. However, they are probabilistic. So there is a certain probability here denoted by these histograms for this neuron to be in state 0, this neuron to be in state 1. And there is also a probability for this weight that is associated to this connection for it to be in state 0 or it to be in state 1. And now, when we take the usual dot product between weights and inputs and pass that through a threshold nonlinearity, effectively, the output of this operation will also be probabilistic and will be associated to the push forward of the probabilities on these input neurons and these weights through the layer function. So now we can try to generalize a little bit this paradigm where we have probabilities associated to weights if we encode our weights as qubits as well. So this is what we could imagine calling a quantum probabilistic neural network. And so the next point would be, how do we choose this unitary U in such a way that we can reuse some of the things that we know from the classical setting? So first of all, we talked about unitary gates, right? So these possible operations that you can do on a quantum computer being only linear. However, as you can imagine, we can in fact implement any Boolean function using these quantum gates, even though they are linear and reversible. And there is the classical example. For example, consider the AND function, right, which given two bits, x1 and x2, computes the product x1 and x2, x1 times x2. So the idea is that to implement this in a reversible and linear way, what you need to do is that to introduce some ancilla register, so this extra line here. And practically, there is a famous gate that does that for you, which is called the Toffoli gate, where you basically, this notation is not important for the moment. But what is important to realize is that what happens here is that you flip this top qubit if and only if both x1 and x2 are 1. And that's precisely what happens when you do the AND function. And so the fact that you now copy this x1 and x2 here means also that this can be implemented in a reversible way. So I went through this example now to motivate the fact that even though in a neural network we have nonlinearities, once we associate to this n qubits the state of a probabilistic bit strings of length n, we can also embed the classical threshold nonlinearity, for example, as a quantum gate. So I'm not going to go through the details here of that implementation, but what I want to point out is that using this notion, we can now embed a classical neural network on a quantum computer. And in particular, we can try now to generalize the architecture of a classical neural network by adding some extra computation that is not easy to compute or simulate classically. So you see here on the right, so we have now added an output line here, which means that the qubits where we store our outputs. We have our inputs lines, and we have our weights lines, weights qubits. So these green boxes here are analogous to the classical probabilistic weights. So here we have encoded now some with the action of some of these green gates, some belief about our weights, some probability distribution, if you want, on the weights as a quantum amplitude. And here on the right, we have this box here, which is an implementation of the classical layer. And in the middle, you have a new somehow piece that is what we introduced in our architecture, which we call a deformation of the classical layer, and we denote it D. So now for generic values of this unitary D, the network becomes classically intractable. So this model cannot be simulated anymore classically. And so we can imagine that this is a possible source of advantage for a quantum computer in order to predict some functions, some classical tasks better than a classical neural network. Unfortunately, we do not have the hardware now to test this hypothesis. So what we did was to try to find values for this deformation circuit D, which are still, quantum, but now easy to simulate. So in particular, we look at the gate, which is the structure that is shown here on the right. So we have now a structure of a gate which is geometrically local, where we entangle or we act only on nearby qubits. And it turns out that using a representation which is called the machine learning tensor train decomposition, or in physics matrix product state representation, which allows you with the number of with the memory that scales now only linearly with the problem size to actually compute exactly the output of this quantum circuit. So all this to say that there are some choices of these quantum architectures that are still tractable classically. And so what we did was to benchmark this classical architecture, classically tractable architecture. And we found improvements relative to the baseline probabilistic binary neural networks for real world data sizes. So we just looked at toy examples like fashion MNIST and MNIST, because of course, even though this is tractable, then you need to backpropagate through the whole architecture, and it can get a computational intensive classically still. But this shows the promise of now deforming this classical architecture with some quantum layers to achieve models that can in principle perform better. Now I would like to switch gears a little bit and talk about photonic quantum neural networks. So this is a new somehow concept we have not really seen it so far in the previous talk. So let me just spend a couple of slides to introduce it. So the idea is that we can encode a real number natively in a quantity, in a physical quantity that is quantum mechanical, and it is the position or equivalently the momentum or the intensity of light, which quantum mechanically are called photons. So here you can see a laser, and this laser produces, it's a source of these photons. So now the idea is that naturally in classical machine learning, there are a lot of things that are not discrete in nature, but are continuous. Think about indeed all the neural network architectures that typically use. And so the idea would be, can we use now this natively continuous quantum variables for processing data that corresponds to some continuous system in machine learning. So mathematically, what we are doing is that we are replacing the qubit. Now, remember, this psi before was a two-dimensional vector. Now, with a function, psi of x, where x now can be any real number. For example, you can have a number a times the state 0 plus a number b times the state 0.01, etc. So any real number can be used as a basis of your system. And now we know that there are some natural unitary gates for the qubit systems. There are also natural unitary gates for these continuous variable systems. And in particular, there is the Z gate of momentum k, which just picks up a phase, which is e to the I kx when acting on the basis state x. And another natural one is the gate x of parameter y, which translates an input x to another output x plus y. And an interesting fact about these continuous variables is that there is a class of states which are interesting that are called Gaussian states. So basically, these are the states for which now this wave function psi of x is a complex Gaussian function. Remember, this function is complex valued, so in general, we can consider Gaussians, but now, you know, of complex mean and covariance, if you want to think it that way. And you can visualize now this complex Gaussians. If you add an extra direction on top of your x, you can add the net direction of k, which is the Fourier basis. And as you can understand, if you just look now at the mean and covariance of the real variable x, this is not sufficient to describe now the complex wave function. So you need another direction, and it's customary to take now the momentum k. And so in this space, your wave function can be seen as a two-dimensional blob, where is the region where the probability is basically greater. And now another interesting fact is that if you put together Gaussian states and quantum measurements, you can have a quantum implementation of the probabilistic inference. So we can start here by encoding with this box here, which I call QGP, which stands for quantum Gaussian process, which is a generalization of Gaussian variable. And at this point here, we create a state psi, and this state psi is such that if you now look at the amplitude absolute value squared, this function here, which now depends on two variables, x1 and x2, will be a Gaussian function. But now if you do a Gaussian measurement here, this one will return, for example, a value x1. And so this state, remember, will be projected onto the basis state x1. But the state of the other variable, which we typically call Q mode instead of qubits in photonic quantum computation, the state of this first Q mode now will be actually described by a probability distribution, which is given by the Gaussian posterior, so the probability of x2 given x1. So now we are going to use this insight to think about a natural kind of data that we would like to process with our photonic quantum computation. And the kind of data we look at is the data that can be considered as sparsely or irregularly sampled. Think, for example, about some medical data. On the x-axis here, you have time, and on this y-axis, you have different quantities that you can measure, for example, in a hospital. And as you can imagine, these measurements can be taken at irregular times. So you don't see a nicely spaced grid here, but instead you see a lot of empty spaces, which means that you do not know what the measurement will have been at the time when the measurement was not taken. As another example of this irregularly sampled data that we would like to discuss is the example of superpixel images. Here you have basically grouped some pixels together, and which have maybe some similar characteristics. And what you end up with is an image where the pixels are not located anymore on a regular grid, but they are now on this more irregular location. And naive discretization, namely just moving these points on a grid, like forcing this to be on a grid or adding zeros here, clearly leads to some discretization error. A better strategy is now to think probabilistically about what could have happened in these specific positions where we have missing data. And so what we can try to think about is how to encode uncertainty in a quantum Gaussian state. So imagine that our data is as follows. We have, for example, 5 or 6 time, for example, points, and we have information about only 3 of them. We call them x1, x2, and x5, and this data is unknown at these other time steps. What we can do now is to try to encode this data using this quantum GP encoding that I introduced before. And now, if we imagine that a measurement of this qubits or Q mode, sorry, where we have information returns these values x5, x2, and x1. What remains, for example, on this top Q mode is a quantum state that effectively, when measured, will encode the probability distribution x6 given x1, x2, x5, which is the Gaussian posterior that is given by the following condition of probability. So that will be the way we encode our data on the quantum computer. What we do next is that we can do some optical operations. Remember, I told you these Q modes are precisely the states that are produced by lasers. And so naturally, once you have some ray of light, what you can try to do, once you have a laser beam, you can try to use some beam splitters or mirrors to actually manipulate your states of light, your photons. And so it turns out that this is a very interesting thing because optical operations can consume a very low power. And so there is indeed some subfield in machine learning which tries to use optical components to implement just classical neural networks. And so the idea that we use here is similar to what has been done there. Mathematically, what's going on here is that you are implementing a sort of a quantum linear layer. So we see here on the left the optical implementation, but you can think about it indeed mathematically as a unitary matrix or operator of the sort e to the I h, where h is now a quadratic polynomial in operators q hat and p hat. And these guys are defined as follows. Q hat is the operator which, acting on a basis state x, will return exactly the value x. So x is an in this cat is an eigenstate of q hat. And instead, this p hat is the so-called conjugate momentum. And so it is defined as the operator such that if you now compute the expectation x p hat psi, this will be the same as acting with the minus psi derivative on the wave function psi. And so here I just have a little bit of a technical one line. If you are versed already in this kind of mathematics or physics, what's going on in a little bit more details, for example, can be seen for an example of one Q mode, and take this Hamiltonian, which is given to -1/2, and then a certain parameter A, and then Q hat P hat plus P hat Q hat. What you can show is that if you now take the unitary operator associated to this Hamiltonian, and you conjugate your position operator Q hat, this will be the same as multiplying your position operator Q hat by a number e to the A. And you can do this computation because you know the commutation relations between Q hat and P hat being I. So if you didn't follow this line, it's not important. I just wanted to give a flavor for those who are experts in the field for what's going on here. And the bottom line is that you are actually operating linearly on the variables Q hat, and therefore this translates to a linear operation on your computational basis. Okay, and so now as the last piece of the puzzle, we want to think about the non-linearities also as unitary gates on a photonic quantum computer. As before, we've thought about the linear gates, so as a certain linear operation on the variable Q hat. Here, the nonlinear gate will also be thought about as the result of time evolution that takes your variable Q hat to another variable, sigma of Q hat, where sigma is the nonlinearity at a later time t is equal to 1. So more technically, we discovered that if you use the following Hamiltonian, which is given by p hat f of Q hat by plus f of Q hat p hat, where f now is a generic function, the evolution of this variable Q hat, so this is analogous to the Schrödinger equation you saw before, is given by the commutator between Q hat and H. And since H contains this f of Q hat, which commutes with itself, with the Q hat itself, this f can be plugged out of the commutator. And what you're left with is just a commutator of Q hat and P hat, which gives I. And the bottom line is that if you take this specific Hamiltonian, the position operator, which is this Q hat, evolves with an ODE that is an autonomous ODE in that variable Q hat. And this means that under this time evolution, you can create a complicated transformation of the variable. For example, we can create a transformation which is implementing the nonlinearity called soft plus, which is a famous nonlinearity in deep learning, which is a sort of invertible version of ReLU. And so it is actually, if you plot it, it's really very similar to ReLU, and it actually functions more or less the same as ReLU. And so with our construction, you can implement the soft plus on a quantum photonic computer by taking this f to be the exponential map. So it's pretty neat. So putting all these pieces together, we have a prescription that starts with producing some states of light with a laser. It uses this quantum Gaussian process idea to encode sparsely sampled data on a quantum hardware. It then acts with this concatenation of linear layer implemented with optical linear optics, together with non-linear optical layers that implement non-linearities. You can do this L times, like we do in classical deep learning, to create more complex representations and more entangled state and distributions in your system. And at the end, you just measure your system, and what you get is a distribution that encodes not only the prediction, which is the mean value of this distribution, but also some uncertainty. And this uncertainty is really coming from the uncertainty you created by having this irregularly sampled data. So you can actually use this uncertainty to reason about the confidence you have on your prediction, given that you had some missing data inputs. Similarly to what we did before, we cannot run this model, unfortunately, at present, because the current photonic quantum computers are too early stage. And so to study the general architecture, we propose we will have to use a photonic quantum computer, and this is a future work. But what we can do is to try to assess the promise of the various ideas that we put together by looking at some classical, limit of that architecture. And so that's what we did. And so in the classical limit, what is happening is that you are just computing a classical push forward of the input Gaussian distribution that you have on your missing data. And so here it's a schematic indeed of this classical architecture, where we have a GP that encodes, indeed uncertainty by this variance about the missing data points in your superpixel images of MNIST. You pass through some linear, nonlinear layers, which indeed creates more complicated distributions. And at the end, you come up with a prediction, which is, again, accounting for the uncertainty for missing data. And in the classical simulation, of course, we need to do something smarter to deal with non-Gaussian probabilities. So what we do is just project back to a Gaussian state. This is not something you have to do quantum mechanically on a quantum computer, because in fact, the quantum computer can actually work with arbitrary non-Gaussian states. Despite this approximation, we find that our method worked very well. And at the time of publication, a couple of years ago, this actually achieved the state of the art for this superpixel MNIST task. Okay, so this brings me to the concluding remarks of my talk. In particular, what kind of challenges do we expect to try to need to solve? So the first challenge is really the core issue here, which is how to establish quantum advantage. So in a nutshell, what we would like to do to establish quantum advantage is to show that the quantum neural network architecture that we propose, for example, is better than any classical machine learning model. For example, for sample complexity or runtime or other metrics we might care about. Power could be also another one, which is maybe easier to assess. But if we think about sample complexity or runtime, there are actually some pretty big hurdles actually in carrying out this program. In particular, the current quantum computers are small, so we cannot really benchmark what we are doing. And the classical neural networks, of course, can be run at a large scale. And another theoretical challenge is that it's very difficult to find theoretical guarantees, even for classical deep learning. So it's going to be very difficult to imagine proving that our quantum neural network is better, say, in generalization error than any classical neural network. There has been progress understanding this question for different tasks, and namely the task of learning with these quantum neural networks from quantum data. As you can imagine, if your data is not classical but quantum, you can have a quantum advantage with the quantum computer, and that has been put on firm. I mean, it's still being discussed, but some interesting results have been obtained recently. So what is left to us? Well, it is left to us to do some small-scale simulations, and an approach that has not been really much explored, but I think is interesting, is also to study the large number of qubits limit. As you probably know, this study of large width classical neural networks has been a very promising theoretical framework to understand deep learning. Think about, for example, the neural tangent kernel as one of the main advances there. But in the quantum case, the behavior of the quantum neural networks in this larger limit has really not been explored much. And so this is an interesting direction, I think. And in particular, there's been recent work in the context of the quantum approximate optimization algorithm. I didn't really introduce this and understand this for the most probably doesn't say much, but it's also a variational quantum circuit of the kind I introduced, this time not for solving a machine learning problem, but for solving classical optimization problems similar to quantum annealing. And so you can actually show that via this large N technique and numerical experiments that there is an expected polynomial speedup for random SAT compared to the state-of-the-art, classical solvers. So that's an interesting thing that we would like to generalize for a quantum neural network case. And another fundamental issue here is noise. As also we heard in the previous talk, qubits are realized at the atomic scale, so it is impossible to isolate them from their environment. And this means that there is a lot of noise that creates faults. And you can see here in this plot that if you do your, for example, quantum neural network training with a noise-free simulation, which corresponds to this red bar, as soon as you start to introduce noise, for example, here noise is 10 to the -3, the accuracy drops significantly. And of course, if you reduce the noise, the accuracy recovers a little bit, but this is a real challenge. The long-term solution is to do quantum error correction, which is a principled approach to noise in quantum computing, but that requires many physical qubits, because now you are encoding redundantly one logical qubit in many physical qubits. And an interesting thing that I want to somehow point out here is that classical computer vision, in fact, can accelerate the progress on quantum error correction. So we have a recent work where we show that if you now have a quantum memory, which is here shown as the state of 3 qubits, and now you act with some noise, this flash, which corrupts the state, for example, by flipping the last qubit. We have developed this neural decoder, which is a classical neural network that allows you to, given a state of this corrupted system, to recover the original state, because the task then is a purely classical task. And to do that, we actually used some notions from group equivariance that have been developed in computer vision. Okay, so here, just this draws me to the conclusion of my talk. I introduced the model of parameterized quantum circuit as quantum neural networks as a promising new model in the machine learning toolkit. And this is going to be more and more interesting as quantum hardware improves. We also saw that we can encode quantum probabilities in quantum states, and in particular, we can use that to encode beliefs about parameters of your neural network. And we also looked at the case where this quantum probability is encoded discretization uncertainty when mapped on a photonic quantum computer. The approach we took in this work was to benchmark some classical retractable limits of the quantum neural network, and this allowed us actually to look at real size data. So it was one of the very few works that actually aims at doing that. And also we saw that for irregularly sampled data, the model that we somehow inspired somehow by the quantum architecture actually can achieve very good state-of-the-art accuracy for that task. And as an outlook, I mentioned indeed that it would be interesting to perhaps study the quantum neural network theory from the large unlimited and comparing that with the classical neural net case. And also, I think another interesting approach at the intersection of machine learning and quantum computing is to use classical machine learning to accelerate the development and the control of quantum hardware. I mentioned, error correction there, but there are also other approaches to quantum compilation and other hard tasks that we need to solve in order to achieve a fully scalable quantum computer. And so with that, I would like to thank you for your attention. Happy to answer any questions you have.
Thank you a lot, Roberto, for that interesting talk and for the short glimpse into the world of gate-based and photonic quantum computing for machine learning. We have time for a few questions now.
Thank you for your inspiring talk. I have two naive questions. The first one is, I wonder how can we train the quantum neural network? Do we need something like a gradient message, or do you have to measure the intermediate layer qubit information? Do you have to make measurement? Sorry, the second question is, can we relate to quantum neural network to Bayesian neural network? Thank you.
Yes, thank you very much. Indeed, these are points that I hinted at, but I didn't really touch upon, so happy to answer those. So first point is indeed, yes, you can imagine using gradient-based optimization. So maybe let me just quickly go back to the slide where we introduced the variational quantum circuit. So I mentioned here, right, that there are these variational parameters, and correctly you understood that this now can be optimized by some gradient method. And so you have, like in the classical case, a loss function, which now depends on this variable y hat, which is your prediction of the quantum neural network. And this y hat here is a smooth function, actually, of your parameters theta in general, because these theta are really just angles that you have in your neural network. And so you can imagine then just doing some gradient descent to optimize it. There are, though, some considerations that come about when you think about this problem. So in particular, there are some optimizers that have been developed to exploit better the geometry of these quantum circuits. So indeed, you can do something a bit more sophisticated and naive stochastic gradient descent, but you're right, that's the main idea. The other question was about Bayesian. That's a very interesting question. I mean, it has actually a lot of ramifications. In fact, a first point is that there are some interpretations of quantum mechanics that really think about the quantum state as a prior that we have about our world, and then these measurements are really just updating your prior to some posterior. And in the case of neural networks, really what we were doing here is very close indeed to Bayesian approach. So in this case, as I mentioned before, classically we put some probabilities on these weights, and you can think about it as indeed a variational posterior for your Bayesian neural network. And so here we are doing something similar. So namely, we are constructing a variational posterior using these unitary gates. But that was a very, very good insight. Thank you.
Thank you a lot for those two good questions. We would need to continue with our poster session now.
Sure.